On a clear night, Beta Pictoris looks like an ordinary bright star. But around it, a young planetary system is still revealing the violent, beautiful process by which worlds are assembled. In July 2026, NASA's James Webb Space Telescope helped astronomers find a planet that had been hiding in plain sight. This is not a story about spotting a tiny dot by chance. It is a story about separating a faint world from the glare of its star, reading the architecture of a dusty disk, and learning how a planetary system can keep secrets for decades. Tonight, we travel to Beta Pictoris, roughly 63 light-years away, to meet a hidden giant called Beta Pictoris d. Beta Pictoris is young by cosmic standards, only about 26 million years old. Our Sun is more than 4 billion years old, so Beta Pictoris is closer to a newborn than a middle-aged star. It is surrounded by a broad disk of dust and debris, the leftover material from planet formation. That disk is one reason the system became famous. Astronomers have watched it for years, seeing a thin, tilted band cross the star. They have also found planets farther out, Beta Pictoris b, a gas giant, and Beta Pictoris c, another world closer to the star. Yet the inner neighborhood remained difficult to map. The problem is contrast. A star is an enormous lamp. A planet is a small, cold ember next to it. Even a giant planet can be overwhelmed by the light scattering through a telescope's optics. The closer the planet is to its star, the harder the challenge becomes. Beta Pictoris d was hidden in exactly that difficult region. It orbits close enough to the star that direct imaging is incredibly demanding. It was not absent. It was simply buried beneath a flood of photons, like trying to see a candle beside a searchlight. Webb changes the problem in two ways. First, its mirror collects infrared light, where young giant planets can glow strongly from heat left over from their formation. Second, its instruments are designed to suppress the star's glare and preserve delicate details around it. The discovery involved observations with Webb's coronagraphic imaging. A coronagraph places an artificial mask over the bright star, allowing the surrounding region to be examined. The technique is not perfect, but it turns an impossible image into a solvable one. Astronomers can also rotate the telescope or use carefully chosen reference observations. Anything fixed to the telescope tends to stay fixed in the data. A planet moves with the system or changes position relative to the background. By comparing images, researchers can identify the signal that behaves like a real companion. The result is a new member of the system's planetary family. Beta Pictoris d is a giant planet, and its detection helps fill the gap between the known inner and outer worlds. Rather than a simple system with one or two planets, Beta Pictoris appears to be a layered laboratory of planetary dynamics. Imagine the system from above. At the center is the hot, bright star. A dusty disk extends outward, made of grains that may be remnants of collisions between planetesimals. Within that disk, several massive planets travel on different orbits, shaping the debris around them through gravity. A planet does not need to touch dust to control it. Every orbiting world creates a gravitational pattern. It can herd smaller bodies, clear lanes, tilt belts, and disturb comets. Over millions of years, those influences leave fingerprints in the shape of the disk. This is why the hidden planet matters beyond its own existence. Its orbit may explain features in the dust that once seemed mysterious. The location of a warp, a gap, or an asymmetry can reveal where a planet has been pushing and pulling material over geological time. Planet formation is not a neat construction project. It begins in a disk of gas and dust around a young star. Tiny grains stick together, collide, break apart, and grow into larger bodies. Eventually, some of those bodies become massive enough to capture gas and become giant planets. But the final arrangement is often chaotic. Planets can migrate as they exchange energy with the disk. They can scatter smaller worlds. They can settle into resonances, where orbital periods form precise ratios. A young system may spend millions of years rearranging itself before reaching a more stable configuration. Beta Pictoris gives astronomers a rare chance to watch that process while it is still comparatively fresh. We cannot observe a single planetary system for millions of years, but we can compare many systems at different ages. Young systems like this one provide snapshots of an earlier chapter in the story that eventually produced places like our own solar system. The new observations also demonstrate why infrared astronomy is so powerful. A young planet is still contracting under its own gravity. That contraction releases heat, making the planet brighter in infrared wavelengths than it would be after billions of years of cooling. The planet may look like a small point in an image, but the light carries physical information. Its brightness can be compared with models of temperature, radius, and atmospheric chemistry. Future observations may reveal clouds, molecular absorption, or changes caused by the planet's rotation. There is an important distinction here. Seeing a planet directly is not the same as taking a detailed photograph of a surface. At 63 light-years, Beta Pictoris d is unresolved. Webb detects its light as a point-like source. The science comes from position, brightness, spectrum, and how the signal changes over time. Those measurements can test competing ideas about how giant planets form. Did the planet grow slowly by collecting a solid core and then capturing gas? Or did a dense part of the disk collapse rapidly under its own gravity? The planet's mass, orbit, and atmosphere can help decide between these pathways. The system may also help us understand why some planetary systems look unlike ours. Our solar system has 4 small rocky planets close to the Sun and 4 giant planets much farther out. Beta Pictoris seems more compact, younger, and more dynamically active. Its planets occupy a different arrangement, reminding us that there is no single blueprint for making a planetary system. And this is where the discovery becomes personal. When we look at Beta Pictoris, we are seeing a possible version of a past that Earth no longer remembers. Long before our planet had oceans, forests, or observers, the young sun was surrounded by its own disk of debris. Worlds collided. Orbits shifted. The system slowly settled into the structure we know today. Webb is therefore not just finding planets. It is recovering lost chapters of planetary history. Each faint companion adds a clue to the rules that govern worlds before they become calm enough for life, or for anything else, to notice them. The discovery also shows that hidden does not mean unreachable. For years, astronomers had strong reasons to suspect that additional planets could be shaping Beta Pictoris. The dust disk was too structured, and the known planets could not explain every feature. Webb supplied the sensitivity and precision needed to turn a gravitational hint into a visible world. More observations will be essential. A single image provides a position. A sequence of images provides motion. Once the planet's orbit is measured more accurately, researchers can calculate its distance from the star, its orbital period, and its role in sculpting the disk. The system may continue to surprise us. New processing methods can reveal companions hidden in existing data. Spectroscopic measurements may identify chemical signatures. Observations at different wavelengths can separate reflected starlight from the planet's own thermal glow. There is also a lesson about scientific discovery itself. The headline may say that Webb found a planet, but the real achievement is quieter and more technical. It required models of the telescope, careful calibration, repeated observations, statistical tests, and independent checks against artifacts. Astronomy advances when a signal survives every attempt to explain it away. A planet is not accepted because an image looks exciting. It becomes convincing when the source appears at the right location, behaves like an orbiting object, and agrees with the physics of the system around it. Beta Pictoris d passed into that larger story. It is a world hidden beside a brilliant star, now brought into view by a telescope operating far from Earth. Its existence makes the system more complex, but complexity is exactly what scientists need. Simple diagrams teach the basics. Real systems reveal the truth. So, when you imagine the famous dusty disk of Beta Pictoris, do not picture empty space with a few planets sprinkled inside. Picture a living gravitational machine. Dust collides. Planets tug. Orbits evolve. Light travels for decades before entering Webb's instruments and becoming a clue. Somewhere in that darkness, Beta Pictoris d is completing another orbit around its young star. From Earth, it is only a faint infrared signal. But that signal tells us that planets can hide in the brightest places, that planetary systems are still under construction, and that the universe has more ways to conceal a world than we once imagined. The next time you see a bright star, remember that its glare may be hiding an entire architecture of planets. With the right telescope, the right wavelength, and enough patience, even a hidden world can step out of the darkness. This is the promise of Webb, not merely to show us distant objects, but to show us how cosmic systems become what they are. Beta Pictoris d is one new point of light. Around it is a much larger story, the unfinished story of planets, dust, gravity, and time.